In June 1982, a fireball erupts in the frozen wilderness of Siberia. The explosion is so massive that American satellites register it immediately. It was said to be visible from space. NORAD analysts scramble to their stations, convinced they're witnessing a nuclear strike on Soviet soil. But there's no radiation signature, no incoming missiles, no military mobilization. Just a pipeline that has torn itself apart with the force of a 3-kiloton bomb. The Soviet Union blames mechanical failure. Internal reports cite equipment malfunction. Western intelligence says nothing at all. For decades, the truth remains buried in classified files, protected by the silence of spies and the pride of empires. But this explosion wasn't an accident. It wasn't sabotage in any traditional sense. What destroyed this pipeline, what created one of the largest non-nuclear explosions ever recorded, was a cyberweapon. This is Blueprint. To understand how lines of code could produce a mushroom cloud visible from orbit, we have to go back, not to 1982, but to a February evening in 1981, in a city defined by cold and secrets. Moscow in winter is brutal, the kind of cold that cracks metal and freezes the breath in your lungs. But inside the French embassy, the air is warm with champagne and conversation. Diplomats mingle, attachés exchange pleasantries, and somewhere in this crowd, a man is about to change the course of the Cold War. His name is Vladimir Vetrov. He's 49 years old, a lieutenant colonel in the KGB's elite Directorate T, the division responsible for acquiring foreign technology through any means necessary. For 16 years, he's been one of the Soviet Union's most trusted intelligence officers, orchestrating the theft of Western industrial secrets across 3 continents. But Vetrov is not here to steal secrets, he's here to give them away. The French intelligence officer he approaches doesn't know it yet, but he's about to receive the most damaging intelligence leak in Soviet history. Over the next 18 months, Vetrov will hand over nearly 4,000 documents. He will expose every agent, every operation, every success of Line X, the KGB's global technology acquisition program. The French give him a code name. They call him Farewell. The documents Vetrov provides read like an inventory of Cold War espionage at its most ambitious. Line X isn't just collecting military secrets, it's systematically acquiring every piece of Western technology the Soviet economy needs to survive. Computer chips, radar systems, telecommunications equipment, industrial control software, machine tools, manufacturing processes. The Soviets are copying Western technology faster than Western companies can patent it. The scale is staggering. In one document, Vetrov details how Soviet agents have acquired the complete plans for the French Mirage fighter jets' avionics systems. In another, he describes the successful theft of IBM manufacturing techniques. A third outlines operations targeting American oil and gas technology, including the sophisticated software systems that control pipeline operations. The KGB isn't just stealing individual technologies, it's building an alternative Soviet industrial base, piece by stolen piece, on the foundation of Western innovation. And it's working. CIA Director William Casey reads the Farewell dossier in his office in Langley, Virginia. The documents confirm what American intelligence has long suspected but never proven. Soviet technological progress isn't organic, it's parasitic. The USSR has been stealing Western technology for decades, and the theft has accelerated dramatically under Leonid Brezhnev's modernization programs. Casey's first instinct is to shut it down, arrest the agents, expel the diplomats, burn the networks. But then someone asks a different question. What if, instead of stopping the theft, they use it? The plan that emerges from this question will become one of the most closely guarded secrets of the Cold War. It will remain classified for over 2 decades, and it will demonstrate for the first time in history that software can be a weapon of mass destruction. The concept is elegant in its malice. The Soviets are stealing Western technology. They trust this technology because they've verified its capabilities in the West before acquiring it. They believe what they steal will work exactly as advertised. So give them what they want, but give it to them broken. The operation targets every aspect of Line X's acquisition efforts. Stealth aircraft designs with subtle flaws that will only manifest at supersonic speeds. Turbine blueprints that will produce vibrations leading to eventual mechanical failure. Space shuttle plans that will lead Soviet engineers down blind alleys for years. But the most ambitious sabotage targets something the Soviets desperately need. Something they're building at tremendous scale across Siberia. Something that represents the future of the Soviet economy. Natural gas pipelines. In the early 1980s, the Soviet Union sits atop the world's largest natural gas reserves. These reserves represent hard currency, the ability to sell energy to Western Europe and acquire the foreign exchange the Soviet economy desperately needs. But extracting and transporting this gas across thousands of kilometers of frozen wilderness requires technology the Soviets don't possess. They need automated control systems, sophisticated software that can monitor pressure, regulate flow, operate thousands of valves across vast distances. This kind of industrial control technology doesn't exist in the Soviet Union, but it exists in Canada. The Soviets approach Canadian companies directly, seeking to purchase the control systems they need. The request goes through diplomatic channels, and in an era of détente and commerce, it seems like a reasonable transaction. But the Canadian government consults with its allies, and Washington says no. The Reagan administration blocks the sale. National security concerns, technology transfer restrictions. The Soviets are left without the systems they need. But Line X has solved this problem before. If they can't buy the technology, they'll steal it. Within months, KGB agents in North America begin targeting the Canadian companies that manufacture pipeline control systems. They recruit sources, they acquire documentation, they copy software. And this time, the CIA is watching. The software the Soviets steal has been modified. The changes are subtle, elegant, designed to remain dormant through testing and initial deployment. The code functions perfectly under normal conditions. It passes every diagnostic. It operates exactly as expected during the commissioning phase. But buried in the program are instructions that wait. Instructions triggered not by external command, but by specific conditions. Conditions that will inevitably arise once the system is operating at full capacity. When those conditions are met, the software will do exactly what it was designed to do. The Trans-Siberian pipeline stretches across some of the most inhospitable terrain on Earth. Thousands of kilometers of steel and permafrost, carrying natural gas from the Urengoy fields in northwestern Siberia to markets in Western Europe. It's the largest infrastructure project in Soviet history, employing tens of thousands of workers, representing billions of rubles in investment. And it depends entirely on automated control systems to function. Soviet engineers installed the stolen Canadian software throughout the pipeline network. It monitors pressure differentials. It controls valve operations. It regulates the flow of gas across distances that would take days to traverse by road. The system works beautifully. For months, gas flows smoothly. The technology the Soviets couldn't buy and had to steal proves just as reliable as they expected. Then summer comes to Siberia. Summer in Siberia is a season of extremes. The frozen ground thaws. Temperatures swing wildly between day and night. Demand patterns shift as heating needs decrease in the Western markets the pipeline serves. These variations create exactly the conditions the sabotage software has been waiting for. The technical details remain classified, but the basic mechanics can be reconstructed from later accounts. The modified code contains what later generations will call a logic bomb. When specific pressure and flow conditions coincide, when valves operate in particular sequences, the software takes actions that no Soviet engineer has authorized. It increases pressure beyond safe limits. It closes valves that should remain open. It defeats the safety interlocks designed to prevent exactly this kind of failure. The pipeline becomes, in effect, a bomb. On a June morning in 1982, The explosion occurs. The fireball rises over the Siberian wilderness, visible for hundreds of kilometers. The force is equivalent to 3,000 tons of TNT. American reconnaissance satellites, constantly monitoring Soviet territory, capture the event in real time. At NORAD headquarters in Colorado, analysts initially categorized the thermal signature as a possible nuclear detonation. The location is wrong for any known Soviet test site. There's no advance warning, no telltale signs of weapons preparation. For tense minutes, military officials consider the possibility that they're witnessing the opening act of a nuclear exchange. But the analysis quickly rules out a nuclear explanation. No radiation, no electromagnetic pulse, no secondary detonations. Just an explosion, massive, visible from space, but conventional. The Soviets say nothing. In Moscow, the explosion is treated as an industrial accident. Pipeline failures happen. The Siberian environment is harsh. Equipment malfunctions. These things occur. The official investigation blames mechanical failure, substandard materials, inadequate maintenance, human error. The reports are filed, the bureaucratic machinery turns, and the incident is classified in the special archive reserved for embarrassments the state prefers to forget. But certain officials know better. Certain analysts, reviewing the sequence of events, the precise combination of failures that produced the explosion, understand that this was not an accident. The probability of this specific cascade occurring randomly approaches zero. Something is wrong with their systems, something fundamental, and they can't tell anyone. Admitting sabotage would mean admitting that the stolen technology was compromised. It would mean acknowledging that Western intelligence had penetrated Line X, that the entire technology acquisition program might be poisoned. It would mean explaining to the Politburo that billions of rubles worth of stolen equipment might be worthless at best, dangerous at worst. The Soviet system, built on secrecy and the appearance of competence, cannot process this truth, so it buries it. But the consequences ripple outward, invisible yet pervasive. Soviet engineers become suspicious of Western technology. They begin double-checking, triple-checking systems they had previously trusted. They start designing their own versions of stolen technology, uncertain which foreign designs are real and which are traps. The efficiency of Line X, the program that had been closing the technology gap with the West for decades, collapses. Every piece of acquired technology becomes suspect. Every stolen blueprint might be a weapon. The sabotage achieves exactly what the CIA intended. It doesn't just destroy a pipeline, it destroys trust. Across the Atlantic, the success is celebrated in the most classified circles of American intelligence. The operation proves that software can be a strategic weapon. It demonstrates that cyber attacks can cause physical destruction on a massive scale. It establishes that infrastructure can be targeted through its control systems. These lessons will echo through the decades to come, but the success raises questions that no one in 1982 is equipped to answer. What are the legal boundaries of this kind of warfare? What happens when these techniques are used against civilian infrastructure? What precedent has been set? These questions will remain largely unexamined for a generation. The operation is classified at the highest levels. Knowledge is compartmentalized. The few officials who understand what happened are bound by oaths of secrecy and the logic of Cold War necessity. The world won't learn the truth for another 22 years. In 2004, Thomas Reed publishes his memoirs. Reed served in the Reagan administration, working closely on national security issues. His book includes a brief but explosive account of the farewell dossier and the pipeline sabotage. The reaction is immediate and divided. Some intelligence professionals confirm the broad outlines of the story. Others dismiss it as exaggeration or misunderstanding. Russian officials deny any sabotage occurred, insisting the 1982 explosion was a routine industrial accident. Historians begin digging. Journalists file freedom of information requests. Former intelligence officers, freed from their secrecy oaths by time and circumstance, begin to talk. The picture that emerges is both more complex and more troubling than the initial accounts suggested. The sabotage wasn't limited to the pipeline. The modified technology spread throughout the Soviet industrial base. Flawed designs compromised multiple systems. The effects ranged from immediate failures to gradual degradations that manifested over years. Some analysts argue that the farewell operation contributed to the eventual Soviet collapse, that the poisoning of their technology base accelerated the economic decline that brought down the communist system. Others dispute this, noting that the Soviet economy faced structural problems that dwarfed any intelligence operation. But one fact remains undisputed. In 1982, the United States deployed a cyberweapon that caused physical destruction on a massive scale. It worked, and it established a precedent that the world is still grappling with today. The parallels to later events are impossible to ignore. In 2010, a computer worm called Stuxnet infiltrates Iran's Natanz uranium enrichment facility. It targets the industrial control systems governing centrifuge operations. It causes the centrifuges to spin out of control while displaying normal readings to their operators. It destroys approximately 1,000 centrifuges, setting Iran's nuclear program back by years. The technical sophistication of Stuxnet is extraordinary. Its complexity suggests state-level resources. Its targeting precision implies deep intelligence about Iranian systems. Its method of operation, sabotaging industrial controls to cause physical destruction, mirrors exactly what happened in Siberia almost 3 decades earlier. The line between 1982 and 2010 runs straight and clear. The concept proven in the Cold War becomes operational reality in the digital age. But there's a crucial difference. In 1982, the sabotage software was stolen. The Soviets acquired it through espionage from systems they knew were foreign and potentially compromised. The attack exploited their own illegal acquisition. In 2010 and beyond, the attack surface is vastly larger. Industrial control systems are connected to networks. Critical infrastructure depends on software that can be reached remotely. The techniques of sabotage don't require physical smuggling. They can be delivered across continents at the speed of light. The world that the Siberian pipeline explosion helped create is one where every network system is potentially vulnerable, where physical infrastructure and digital infrastructure are inseparable, where the distinction between peace and war, between espionage and attack, becomes increasingly blurred. Vladimir Vetrov, the man who made it all possible, doesn't live to see these consequences. In 1983, his behavior becomes erratic. Personal problems compound professional pressures. He murders his mistress in a Moscow park, attracting exactly the kind of attention he cannot afford. The investigation leads inevitably to his espionage. Vetrov is arrested, tried in secret, and executed in January 1985. The Soviet Union never publicly acknowledges his betrayal. The damage he caused remains buried in classified files. But his legacy endures. The 4,000 documents he provided exposed the extent of Soviet technological dependence. They revealed the vulnerability of systems that seemed secure. They demonstrated that the greatest threat to an intelligence operation might come from within. And they enabled an act of sabotage that would take decades to fully understand. The question of casualties remains unresolved. Thomas Reed's accounts suggest the explosion killed no one. The pipeline, he writes, was in a remote area, far from any population center. The destruction was massive but contained. But Soviet record-keeping from the era is incomplete and often unreliable. Some researchers argue that workers were almost certainly present in the vicinity, that maintenance crews and monitoring personnel would have been nearby. Others note that the Soviets had every reason to minimize any casualties, to avoid questions about what had actually occurred. The truth may never be known. The explosion happened in a place with few witnesses and fewer records. The Soviet system that might have documented casualties was invested in pretending the event was mundane. The American system that caused the explosion was invested in keeping the entire operation secret. What remains is the event itself, a fireball over Siberia, an explosion visible from orbit, a demonstration that code can kill. The ethical dimensions of the operation resist simple judgment. On one hand, it targeted a totalitarian system engaged in systematic theft of Western technology. The sabotage struck at infrastructure, not people. It degraded Soviet capabilities without direct military confrontation. It may have hastened the end of a regime responsible for immense suffering. On the other hand, it established precedents with troubling implications. If pipeline control systems are legitimate targets, what about power grids, water treatment plants, hospital networks? The logic that justified the Siberian sabotage could justify attacks on any computer-controlled infrastructure anywhere in the world. The distinction between military and civilian targets, already eroded by 20th century warfare, dissolves entirely when the weapon is software. A logic bomb doesn't distinguish between soldiers and civilians. A corrupted control system doesn't verify the age of its victims. These questions seemed abstract in 1982. They seem considerably less abstract today. The modern world runs on industrial control systems far more complex and interconnected than anything that existed during the Cold War. Power plants, chemical facilities, transportation networks, water systems, telecommunications infrastructure. All of it depends on software. All of it is potentially vulnerable to exactly the kind of attack that destroyed the Siberian pipeline. The nations that possess these capabilities keep them secret. The techniques are classified. The operations are compartmentalized. The few incidents that become public, like Stuxnet, represent only what could not be concealed. But the basic reality is clear. Every major power now possesses the ability to reach across borders and destroy physical infrastructure through digital means. The capability demonstrated in 1982 has been refined, expanded, and deployed in ways that remain largely invisible to public scrutiny. The Siberian explosion was a beginning, not an end. There's something almost quaint about the original operation now. The sabotage required physical theft of software. It depended on the Soviets' own espionage channels to deliver the weapon. It took months to prepare and couldn't be recalled once deployed. Modern cyber weapons are faster, more precise, and far more numerous. They can be updated remotely. They can be deployed in minutes. They can target millions of systems simultaneously. But the fundamental principle remains unchanged. Software controls physical systems. Compromised software can cause physical destruction. And any system sophisticated enough to be useful is sophisticated enough to be dangerous. The men who conceived and executed the farewell operation understood this with a clarity that seems prescient in retrospect. They saw that the nature of technological warfare was changing. They recognized that infrastructure would become a battleground. They grasped that the weapons of the future would be invisible. They were right, and the world they helped create is now our world. In the depths of the Siberian wilderness, the pipeline has long since been repaired. New software runs the control systems, software developed domestically rather than stolen from abroad. The gas flows again, as it has for decades, feeding the economies of Russia and Europe alike. But somewhere in the archives, in the classified files that governments prefer to forget, the records remain. The farewell dossier, the sabotage plans, the satellite imagery of a fireball rising over the taiga, a reminder of what was possible and a warning of what still is. The explosion in 1982 lasted only seconds, but its echoes continue to reverberate through the present moment, through every network system, every automated process, every piece of critical infrastructure that depends on software to function. We live now in a world those echoes created. The question is no longer whether such attacks are possible. That question was answered over a frozen Siberian landscape more than 4 decades ago. The questions now are different and more urgent. Who controls these capabilities? What restrains their use? What happens when they fail to work as intended? What happens when they work exactly as intended against targets we haven't anticipated? These are not theoretical concerns. These are the defining challenges of 21st century security, and they trace their origins to a moment when American intelligence officers looked at Soviet espionage and asked a simple, devastating question. What if we let them steal it but make it broken? The answer to that question is still being written in power grids, in financial networks, in hospital systems, and voting machines. In every piece of code that controls something physical. In every connection between the digital and the material world. The Siberian pipeline explosion was a proof of concept. The experiment worked, and the results, for better and worse, belong to all of us now.